to introduce you to the concept of thinking about entropy at the molecular scale, I want to introduce you to a very simple sort of framework known as the two-state system. And so the two-state system is something we're going to revisit quite a lot in this course. And essentially what it does is it describes a system of molecules or group of molecules that can exist either in a low energy ground state or in a high energy excited state, right? And so to sort of think about it, I want to draw for you a plot that looks like this, where here are our two axes, and really on the y-axis we're going to have two different energy scales, where here energy is equal to 0, and here the energy is going to be equal to some constant called B, right? And the x-axis, it doesn't necessarily represent any sort of property, but it just describes the position of different molecules. And let me draw this better. These need to line up. Where molecule 1 can either be in the ground state or it can be in the excited state. And molecule 2 can also be in the ground state or in the excited state. And so we could describe, here's an example from the textbook of, a couple of molecules organized into this two-state system. And you could see that some molecules are in the ground state and some molecules are in that excited state. Right? So each molecule has an energy associated with it, but the overall energy of the system, the internal energy, is going to be the summation of the individual energies of each of the different molecules. Okay? Alright, so that's the sort of premise of the two-state system. So with this system, let's go through some examples of some basic calculations. And so let's consider the case where in our two-state system we have three different molecules. And so what we want to calculate is how many microstates do we have in which the total internal energy of the system is either equal to 0, B, 2 times B, or 3 times B. Alright? So that's the idea here. Alright? And so to visually sort of see this, we could also just consider the different sort of microstate combinations that can exist for each of the total different energies. Right? And so for the case where our total system energy is equal to 0B, if we think about the arrangement of three molecules in the system, there's really only one arrangement that could give us a sum of 0. And that's the case where all of the molecules are in that low energy ground state. If we think about the possible combinations that could give us an energy equal to just 1 times B, we have three different combinations. Either the first molecule can be excited and the other two are not excited. The second one can be excited, or the third one can be excited. Right? So those are the different possibilities for just getting B. In order to get 2B, we could either have two molecules next to each other excited, or each of the molecules on the end excited. And to reach 3B, all of the molecules here need to be excited. Right? So this is how we could just sort of count it. Right? But in order to generalize our calculation, if we were dealing with a system of 10,000 molecules, we want some way to be able to calculate it more easily. To do that, we could go back to our sort of binomial sort of calculations. And so essentially what we want to do is we want to calculate the number of microstates for the different molecules in our system. And so the way we would describe that is we have the total number of molecules, and because there's really only two states in the system, you're either excited or unexcited or excited, we could do the microstate calculation by just using the binomial coefficient. So in this case, we would either have some number of molecules that are excited, so that's represented just by this U divided by B, where U is that total internal energy of the system. And then we have the molecules that aren't excited. Okay. All right, so the way this is worked, let's consider the case where our total internal energy is equal to 0. And so here we have our 3 molecules. And then if U is equal to 0, this ratio would also be equal to 0. So we have 0 factorial. And then here we would take n minus 0, right? And so, if you remember, by definition, the 0 factorial is just equal to 1. Here we have 3 factorial. And then here we have 3 minus 0 factorial, which is also just 3 factorial. So as a result, these cancel. And what we get is that the total number of microstates that could give us internal energy equal to 0 is just 1. Right? So this is what we calculate. And if we think back to our picture here, we see that it's consistent. There is only 1 microstate that we could get. And so if you go through this calculation for the other sort of internal energy possibilities, you would get numbers that match the picture. Okay? All right, and so that's how we would estimate the number of microstates in the two-state system.